It has led to groundbreaking discoveries about our solar system, the stars, and galaxies far away. Space technology has also improved life on Earth in many ways, from satellite communications to weather forecasting and GPS systems that help us navigate. Therefore, it is a time to learn, explore, and be inspired by the endless possibilities that space offers. So, one of the most exciting space missions happening right now is the JUICE mission. JUICE stands for Jupiter Icy Moons Explorer, and it is a spacecraft designed by the European Space Agency (ESA) to explore Jupiter and its three largest moons, Ganymede, Europa, and Callisto. These moons are fascinating because scientists believe that they have huge oceans hidden beneath the icy surfaces, which could support life. By exploring Jupiter and its moons, JUICE aims to answer big questions about how our solar system works and whether other places in space might have the conditions for life. It's an exciting journey that brings us one step closer to unlocking the secrets of the outer solar system. I would hereby like to start the Space Week off with our first webinar, JUICE, The Long Road to Jovian System, presented by Mr. Alessandro Atzei. Mr. Alessandro Atzei holds a master's degree in space systems and rocket propulsion engineering from TU Delft. He has been with the ESA since 2003, serving as a study manager for Jupiter feasibility studies until 2007, a spacecraft system engineer for the Gaia Observatory until 2014, and currently works as a payload systems engineer for the Jupiter Icy Moons Explorer, that is the JUICE mission. Thank you, sir, for being a part of NSS Mumbai. Over to you.
Thank you very much. So in the next hour, let's say, I'm trying to give you an idea of what it's like to embark on a mission to Jupiter. So from the early stages until the launch and after. And in order to do this, I would like to switch to the presentation, which is disabled at the moment. Maybe you can give me the rights to share my screen.
Yes, sir.
Yeah, there we go. Can you see my screen?
Yes, we can see your screen.
Okay. Very good. So the title for this talk is The Long Road to the Jovian System. And I would like to emphasize on this because before launch, there's a lot to happen before we can actually go and be on our way to Jupiter. There was already a short introduction about who I am, so I'll skip it. At the moment, I am a payload manager for the Envision mission to Venus, but until last year, I was indeed one of the payload system engineers for the JUICE mission. Now, the JUICE mission is the first large mission of the ESA science program. It's called Cosmic Vision, and it focuses on Jupiter itself and the three icy moons, Europa, Ganymede, and Callisto. So the importance of the mission is really to try to understand better what's going on in the icy moons and Jupiter itself. JUICE is part of three missions that are visiting Jupiter in about the same time. We already have Juno from NASA, which was launched and arrived at Jupiter in 2016, which is really focusing at the moment on the atmosphere of Jupiter. So it's in a polar orbit and continuously reducing the inclination and taking high resolution imaging of the planet itself, and to really understand better the gravity, magnetic fields, and the atmosphere. The next is JUICE. JUICE was launched last year in April. And JUICE will focus really, as I said, on Jupiter itself, but also the three icy moons. And next week, NASA will launch the Europa Clipper mission. And the Europa Clipper mission is really going to target on Europa. So they will be in a highly elliptical orbit around Jupiter, but having an orbit that intersects regularly Europa. So what are the science objectives for JUICE? So you could say twofold. One is the exploration of the Jovian system, so the atmosphere, the magnetosphere, also understand all the moons and the ring system, because there is a ring system, even if less pronounced than from Saturn. And basically to study Jupiter and its system as a kind of laboratory for solar system research, because Jupiter in the end has the same building blocks of stars like our sun. However, it didn't get massive enough and the gravity didn't get strong enough to start nuclear fusion. So in a way, you could see Jupiter as a very small star, even though it's a failed star because it doesn't have the fusion, and all its moons as kind of planets, because it's already very difficult to study our solar system because it's so large. But by focusing on a relatively smaller area like the Jovian system, you can see the interaction between a massive body like Jupiter and the moons around it. So it really gives us more information about the evolution of the Jovian system, which can then give lessons learned also for solar systems. And the other part is really the exploration of habitable worlds. So we will be focusing at the end mainly on Ganymede as a planetary object and maybe a source of a habitable environment. We will also study Europa's recently active zones, and then the furthest of the three icy moons, Callisto, which is almost unchanged since many centuries and eons and much more. So it would be a kind of a study of the early Jovian system. And when we're talking about habitable worlds, it's not that we're going to look for actual life, but we are going to look for the indicators of life, the building blocks that we need for life as we know it. So the water, essential elements, the energy itself, and a stable environment. So these are things that we are going to study with JUICE. To put things in perspective on the sizes of the moons, the icy moons, here you can see Europa. Here on the bottom, you can see Callisto. So Europa is about the size of the moon. Callisto is about the size of Mercury. And Ganymede, which is really almost, well, it's a bit smaller, but it's starting to approximate the size of Mars. So these are huge moons. They are not just small ones. And we think from earlier missions and observations that these three icy moons that consist of an icy mantle and in the core still liquid water. And why liquid water? Liquid water because they move around Jupiter. Jupiter has enormous gravity. So by moving in a perfectly spherical orbit around Jupiter, you have a part where you get very close, let's say, or relatively close, and relatively far. And these variations in gravity are basically forming a kind of a push-pull. So it stretches when you get close to Jupiter, and when you get further away, it compresses again. And this stretching and compression creates friction, and the friction generates heat, and sufficient heat to melt the ice inside and form an ocean. So these oceans have already some key building blocks of life as we know it. It has a stable environment. It has a temperature that allows for liquid water. And what we are going to study is, does it have all the other building blocks that we need? And for this, we have the JUICE mission that is going to try to answer these questions. And to give an idea of the timeline of such a mission, why does it take so long before you can actually launch? And after launch, why does it take so long to actually get there? You can see this short summary. Basically, from 2003 to 2007, we had what we call the technology reference studies. And during this time, we were really focusing on the technologies that you need to enable a mission to Jupiter. So It's not so much the study of the actual mission itself, but really identifying the technologies that you need, such as special solar cells that work very far away from the sun in very low temperatures with high radiation. But also you can imagine the models for the radiation environment that are needed to model the doses that the components will be encountering and will be used to dimension the design of the mission. And other things are the navigation cameras in order to be relatively independent, autonomous, because it's so far away that you cannot have real-time commanding of the space. So all these kind of technologies were identified to make sure it was available on time for the JUICE mission. So then in 2007 to about 2014 was the next step in which ESA issued a call for proposals for new missions. And then from these calls of proposals, there was a selection done. And one part of the scientific community was requesting a mission to Jupiter to study the science goals just discussed. And the next step then is to identify a mission and to select the instruments and start the conceptual design of these instruments. And when this is far enough detailed, so studied in sufficient detail, it's time to adopt a mission and to give the go-ahead to actually build it. And this happened in the end of 2014, beginning of 2015, where the actual development phase started and then ended in the launch campaign of JUICE. So from 2015 to 2023, the JUICE spacecraft basically was being born, let's say, studied in detail and built and tested. And this phase also included the difficult COVID times, and would in the end cost us 1 year on our schedule. But still, it's a very reasonable and actually quite a good, for such a large mission, a good timeline to develop such a mission. So last year, in April 14th, we launched JUICE. And since then, it's traveling in order to arrive at Jupiter in 2031. And I will explain a bit more why it will take so long to get there. So from 31 until 35 is the nominal mission, and there is the possibility, if the resources allow it, to extend that to, let's say, 37. So when you talk about JUICE, actually there is a whole program. JUICE itself is a spacecraft, but you have many elements that form the mission. And these elements are the spacecraft, the JUICE spacecraft itself, built by Airbus. There's a launcher, the Ariane 5 ECA, that brought us into the trajectory needed to start the mission. We have the ground stations that communicate with the spacecraft, and we have 3 of them dedicated part-time to the JUICE mission. And then, of course, we have the operation center, the Mission Operations Center in Darmstadt in Germany, ESOC, where the spacecraft is commanded. And then once we start really planning and executing the science mission, we have the Science Operations Center in close to Madrid in Spain, where all the missions are being coordinated. And the coordination is then done with the scientific community themselves. So all these different groups and players are part of what we call the JUICE program. So coming back to the spacecraft itself, in order to be able to perform the mission and to actually achieve the science goals, we had quite a few challenges. And one of them was the low power. So the low power of the spacecraft is not due to the solar rays. It has huge solar arrays. I'll show you later, but almost 90 square meters of solar arrays. But it's so far from the sun, 5 times further than Earth is from the sun. And that means that the sunlight is about 25 times weaker than the sunlight, the intensity of the sunlight at Earth. So we need 25 times the size of a solar array that would be sufficient on Earth. So that's already a challenge by itself. And the solar cells have to be really specifically built to operate in a very low intensity and low temperature environment. Low temperature is another point, the harsh temperatures. When you get to Jupiter, it can get down to minus 230 degrees, in which the whole spacecraft needs to survive. And the heaters there should be working despite having limited amount of power. But at the same time, we have a flyby next year of Venus. And Venus is very hot, close to the sun, reflects a lot of sunlight. So we can look at temperatures of plus 250 degrees. So the spacecraft, even though it needs to go and needs to be designed for the cold of Jupiter, also needs to survive the hot case of Venus. So we needed to design for both. And that was quite a challenge. So special insulation was designed to cope with both, and a lot of testing was needed. We already mentioned the long distance. So the long distance, which is hundreds of millions of kilometers from Earth, means that we needed a very large high gain antenna, a dish of 2.5 meters of size. And also, it takes a long time for a signal to come to you and be sent back. So if you get a signal saying that there is an issue with your spacecraft, you cannot immediately fix it, because it already took about 45 minutes. And even if you can reply immediately, by the time it comes back to the spacecraft, 1.5 hours are gone. So the spacecraft needs quite a high level of autonomy. But the biggest challenge really is the high radiation. The high radiation really is the driver for the spacecraft, because the electronics need to be able to survive. And for this, we needed to apply a lot of shielding, including volts, in which we really lined a box in which we put as much electronics as possible with lead. This just to absorb the majority of the radiation. So these were the key challenges for the mission. And it resulted in this spacecraft. So at launch, it was more than 6 tons. The dry mass was about 2.5 tons, and all the rest, about 3.6 tons propellant. As I said before already, we needed about 88 square meters, so almost 90 square meters of solar array surface, which at end of life will barely create 800 watts. So you cannot even run a microwave on it, despite the enormous amount of solar cells, just simply because of being so far away from the sun and also being in such a harsh environment. We have a memory that at the end of mission will still be able to hold about 1.25 terabits of data, and the data rate per day is about 1.4 gigabit. So these are the key design parameters for the spacecraft. So the mission had to be able to perform and to be designed this way in order to be able to provide the data and the science that is gathered by the instruments. So the way it looks is what you see here. So the huge solar arrays, and to give an idea of the size, to scale a person would more or less be the size with respect to all the rest of the spacecraft. Most of the instruments would be on the top deck, still also quite some probes, Langmuir probes, all kinds of deployable structures like the radar antenna and the magnetometer boom. And what does the instrument suite look like? So in the end, we had 10 instruments on board, and it varied from optical cameras to spectrometers, sub-millimeter wave instruments, radar sounders, laser altimeters, radio science experiments, magnetometers, and particle physics and plasma wave instruments. So it's a comprehensive suite of instruments that has never flown before, really to study all the aspects of the Jovian system. So, and what does this look like when it's being built? So this is the core of the spacecraft, where you see a cylinder in the middle containing all the propellant tanks. And here in the foreground, you see one of the so-called vaults that I mentioned before. So these are boxes lined with lead on the inside, in which most of the electronics that do not need to be exposed to the outside are stored, so that they are protected against the harshest part of the radiation caused by Jupiter. Because to give a very simplistic maybe view, but a person would already receive a lethal dose of radiation within 7-8 minutes. So it's really not an environment that is good for humans, but also not for electronics and robotic explorers like JUICE. So this is something that we really had to design for. Here you see the spacecraft once it was already built up quite a bit in Germany before it was sent to ESTEC here in Noordwijk, where we did the environmental test campaign, or at least part of it. And here you see it in ESTEC when we were finalizing all the installation, the final cabling, everything that was needed in order to do the thermal balance and the thermal vacuum campaign, the TBTV as we call it. So once everything was ready, and this is a huge effort of many, many people, we went to the LSS, as we call it, the Large Space Simulator here in Noordwijk, where we can put the entire spacecraft inside a huge chamber, which you see here from above. And we lower the spacecraft inside this huge chamber, which has a big lid, which is seen in the background, which can be just hoisted on top of it, closed. Then you can make it vacuum, and you can start simulating space also by simulating the sun. As you can see here, there is light coming from this side, this opening, and it's basically enormously strong xenon lights that really can mimic the sun. So by switching on more and more lights, you can have an equivalent lighting of the sun, in this case for the conditions at Venus. So on this side, you get extreme high temperatures, and on the other side, in the shadow, it will be extremely cold. This can be a difference of almost 500 degrees. So these kind of tests that you cannot do outside of such a chamber are done to verify that the spacecraft has been designed properly, to verify that the models that we have are predicting the correct behavior, and if not, we need to tweak it and need to correct it. So this was the spacecraft at the end of the campaign, and just to give an idea of the size of JUICE, you see a person here, and you see the spacecraft without the solar rays, obviously, above it. So it's really one of the larger spacecraft that we have built. Once we completed the testing in ESTEC, we had to squeeze it into a container, because this container is one of the limiting factors of the spacecraft, because a container needs to fit in an Antonov airplane in order to be able to transport it first to Toulouse and then afterwards also to Kourou, where it was launched. And I can tell you that this is really just fitting. So that's quite an exciting moment when you have to squeeze it in. So then we transported it to Toulouse, where we did the final part of the test campaign. Here you can see, for instance, this ring. And this ring is the launch vehicle adapter, which you connect to the spacecraft to the launcher. And then after the end of the launcher reaches its trajectory, this ring is released and the spacecraft floats away and starts its mission. But of course, this release is quite violent. It's basically a clam band that needs to be released with pyros. So you need to simulate that to make sure that everything goes well and the spacecraft can survive these loads. So basically, you fire the pyro valves and this ring falls down on these carpets. The next test is the vibration test, and basically where you put this what feels like fragile spacecraft on a big shaker, and then you simulate the vibration of the launch, and you hope that everything survives, nothing falls off. And luckily, this was the case. And then the next test in the environmental campaign is the acoustic test, basically simulating the sound of the launch, and mainly when all the reflection of the engine sound are reflected from the launch pad onto the fairing and the spacecraft. So all these kind of tests that are needed to make sure that the spacecraft behaves properly and survives the launch and afterwards. And here you can see the top deck with the instruments. You can see some protective cover to avoid that particles will contaminate the instruments. And these are very complex and important tests. Also very important is the deployment of the solar rays. Here you can see the spacecraft on the left-hand side, and this was once the solar array was partly deployed, and partly because you cannot deploy the side lobes. Here you can see what it really would look like when it deploys. It forms a cross shape, but the two outer ones you cannot test in this configuration. However, you need to be able to give the command of the deployment and make sure that the solar arrays will deploy once they are launched. Another extremely important test is the electromagnetic compatibility. So in this test, you make sure that the spacecraft basically doesn't disturb itself, or I should say that one unit doesn't disturb other units so that everything can work properly. And this is the only time that you can actually see the spacecraft with a fully deployed RIME antenna. So this is a 16-meter boom, 2 times 8 meters, that emits a 9 megahertz signal that allows you to go through the upper layers of the ice and hopefully deep enough to even detect the ocean at Europa, or at least pockets of water, depending on how the actual surface and subsurface is formed. And the other major challenge was the magnetic cleanliness. We had extremely sensitive magnetic sensors. And the last thing you want is that the spacecraft emits so much magnetic interference that you're not able to measure the magnetic fields outside. So to make sure that this was the case, we had very complex and very delicate instruments measuring the emissions of the spacecraft to make sure that we were within the requirements, which we were. But this wasn't really, can say this is the cleanest spacecraft from an electromagnetic point of view ever flown. So once this was done, all these years of testing were completed. It was time for the spacecraft to leave Europe and to be put on the Antonov 224 and sent to Kourou. And as you can see, this container barely fits inside. So it's really basically driving the dimensions of the spacecraft. And after an uneventful and as we always say, boring is good, flight, we arrived in Kourou, where it was unloaded and transported to the CSG, the Centre Spatial Libyen, where the spacecraft is doing its final preparations before being mounted on the launcher. And here you can see the solar rays really folded away perfectly to be able to, despite the huge size, be able to be fit into the fairing. And then here you can see one of the last images of the spacecraft when the final inspections were being made, cleanliness inspection, make sure that everything is the way it should be, because once it's launched, you can't do anything anymore. So you need to make sure that everything is the way it should be. So then everything is ready. We pack everything and we go to the launcher. So and here you can see JUICE mounted on the top of the launcher, and then the fairing mounted on top of it, and then being moved to the launch pad. This is, of course, very much accelerated, but else this would take too long. And then you can already see quite some clouds, and indeed the first launch attempt we had to scrub because the weather was not good. So we had to wait one more day until the 14th of April. But then and this was the moment that we were on our way to Jupiter. The 8-year cruise phase started, and the launch was perfect, was flawless. So we didn't even need to make any corrections of the orbit. So it was really exactly what we needed in order to be on our way. And what happens then is what you see here, the initial deployments. Oh, sorry. There we go again. So you have the initial deployments that are done autonomously. Basically, the unfolding of the solar panels, and then you will see also the unfolding of the medium gain antenna. And this is very important that this happens without intervention from ground, because if you're unable to establish a connection for whatever the reason, and the spacecraft doesn't have the solar rays deployed, obviously you run out of power and the mission ends there. So without any intervention, these deployments that you just saw here, slower of course, but took place, and that went all fine. And then we had the deployment of the medium gain antenna here, and then all the subsystems were checked out. The propulsion systems, the AOCS systems were enabled, and the spacecraft was put in a stable configuration. And this LEOP, the launch and early operation phase, lasted a bit less than a day, which is very fast, and everything worked flawlessly. And then the next phase was the commissioning phase. And the commissioning phase was the first step was really the deployment of all the appendages of JUICE, which should have been like this, the deployment of the RIME antenna, 2 booms that in a sequence, a very specific sequence, would be deployed. And when that was complete, we had the mag boom, the 10.5 meter boom with all the magnetometer hardware and the Langmuir probes. All this had to be deployed so that all the instruments are able to work the way they should. So this is what should have happened. And here you can see the monitoring cameras that we installed to monitor all these deployments, taking some pictures also with the Earth, making some very nice images. And especially you can see here the RIME antenna nicely folded, ready for the deployment that came next. However, not all went perfectly. Everything was going very well, very pleasantly, very smoothly. However, at a certain point, we started the key deployment of the RIME antenna, and here things didn't go as planned. So here you can see the RIME antenna in its actual position, folded neatly away on the top of the spacecraft, and this is what it looks like. So 2 booms folded away in segments, in 4 segments, which would have to be deployed in sequence. And as you can see here, this is what it looked like in reality. And here you see the importance of such a monitoring camera, because you can see exactly what it looks like, and you can see that everything is neatly in place, survived the launch, nothing has moved. So we were happy to start with the deployment. And as a reminder again, this is what should have happened. So you deploy from both booms the first part, and then 1 boom, you deploy 1 segment and the last segment, so that you have the full 8 meters out, and then you do the same with the other boom. 1 and 2, and then we're in business, and we have this 60-meter antenna ready to generate the signal needed. So that's what should have happened. But now we go to what did happen. So I try to speed up a bit, but to give you an idea, so this is the cross-section of these booms. This one stays in place, and these are the 3 segments that need to be deployed. So the first step is to activate these non-explosive actuators, NEAs 1 and 2 here, and then you get the deployment of the -1 and the +Y1 booms. And this is what happened. So you see, here you see 4 booms on your image, and the next image you see only 1, 2, 3. So this went flawlessly. So 1 boom is deployed towards the right of the screen, and the other is deployed to the left of the screen. This you cannot see, but you can see the center part. It was very cold, -80 degrees. So that was a bit of a surprise, but it worked. So we went to the next step. And this is where things didn't go as planned. So we activated the NEA, the non-explosive actuator 4, which should have released this -Y2 segment. But as you can see, nothing happened. It stayed in place, no movement. So we studied the images, we consulted with all the experts, the manufacturer of the boom, of the spacecraft, our team, and there was an intense engineering phase that lasted in the end 2.5 weeks, where we really went into the details to understand what's happening. And you have to keep in mind that you are in space, so you have very little chance of fixing things, so you need to really think well what you're doing. So the next thing that we tried as a first recovery attempt, we thought, okay, let's release also the next boom, the minus Y3. So hopefully that one will push out this one if it's just stuck because it's maybe too cold or a bit glued to the side. But nothing happened. As you can see, we still see the 3 booms. And now we knew we had to be very careful, because we could already scratch one theory, and now we had a decision tree of what do we do next, depending on what is the problem. And here is the importance also of having these cameras, because you could see exactly what happened when you tried to actuate something. And by seeing small movements, we could deduce where it was stuck. And we could see that it was really stuck in place in this point here. So the next thing that we tried then was to heat it up a bit. Instead of the minus 80 degrees, we tried to go to minus 44. And this required the spacecraft to be tilted towards the sun so that we could heat up this area where the boom was stuck. But this is very dangerous, because it also means that you're starting to expose other instruments to sunlight, and you want to absolutely avoid to damage other instruments in order to save one. So this was a perfect example of working together with all the instruments, all the engineering teams, and we found a way to have a maneuver that was deemed of no risk to the rest. And we heated it up, and then the next thing we did was the deployment of the huge mag boom, the 10.5 meter magnetometer boom. And the idea was that by deploying the magnetometer boom, you cause a vibration through the spacecraft, and this vibration hopefully would release the stuck boom. But again, this was not the case. And on the one hand, it was bad news. On the other hand, this really helped us to pinpoint the problem, because we were quickly homing in on what we thought was the real cause. So we did one more test to make sure that we understood. And even if it sounds strange, we didn't think that this would help. If our theory was right, this shouldn't help. But it's again an intermediate step to confirm the hypothesis. And that was by firing the main engine a few times very quickly to induce a vibration through the spacecraft and to see if it would come loose. And again, it didn't. But in this case, it convinced us that we knew what was going on. And it was this. The good thing of having engineering models on Earth is that you have something that you can check and test to see what's going on. So this is an identical model that you have on Earth. And we noticed that under certain conditions, there was a possibility of, here you can see these springs. These springs keep the boom segments in place. And the idea is that these actuators are switched on. And then, like you see on the right side, this pin is pulled out by a spring and releases this element. However, on the other side, you can see that the pin is still sticking out. So the spring is stuck behind it and cannot move forward. And if it doesn't move out of the way, it means that the boom doesn't deploy. So now that we knew it, we tried on Earth, how do we disentangle it? And we found out that there was only one thing we could do, and we only had one chance. And basically, that's what you see here. We had one more non-explosive actuator from the other boom, but this actuates by melting, basically, a material, and then a spring with a lot of force jumps back. And the force of this spring was enough, on Earth at least, to release this stuck pin. And this you can do on only one time, because we only had this one NEA left on this part of the boom. So after making sure that the conditions were optimal for success, we came at the end of the 2.5 weeks to the point that we went for it. So we prepared everything. We heated again the bracket to give it the best chance of success. And then we actuated the NEA number 6. And then we waited for the image to come in. And the first image that came in was this one. Again, nothing happened. And just when we thought that it didn't work, the next image came in. And the next image showed this. So you have to look very carefully, but basically the 3 booms that used to be here in front are gone. And you now see the 2 booms from the other side still. So it had worked. And this was a major relief because we now knew we were in business. And basically you can see it from the other monitoring camera on the other side of the spacecraft. You can see with quite some force and in not exactly the way that it should have, because you're releasing 2 elements at the same time, but you can see the antenna deploy. And then we had to deploy the last one from the other boom, which also, because we had actuated in a different sequence, also released quite violently, as you can see here, but it still released, it locked in place, and now we were in business. So with this adventure, let's say, that cost us quite some gray hairs, we managed to be ready to proceed our mission. So all the instruments were checked out, everything worked perfectly fine, and we were ready to focus on the next phase, which is the interplanetary tour. And that's what you see here. We have a very complex cruise phase. It's a cruise phase that lasts 8 years, started last year, and just 2 months ago in August, we had the first gravity assist sequence, which was first ever, because it was a combination of first a gravity assist of the moon and then of the Earth. And I'll explain later why. The next one will be in a year from now, in August 25, which will be a gravity assist of Venus. Then we have a year later another one of Earth, and then 2.5 years after that we have a flyby of Earth again, and then only we have enough energy to get to Jupiter and do the Jupiter orbit insertion, and then start the actual mission, which will be first a transfer to Europa, where we will do 2 flybys to make detailed imagery and measurements of Europa. After which we leave this orbit, which is very dangerous for a spacecraft because it's very high radiation being close to Jupiter. We go into a high latitude phase, which allows us to study the poles of Jupiter. And after this, we start the mission towards Ganymede, where we capture an orbit around Ganymede and then go to a circular orbit. And originally we would go to a 500-kilometer orbit, but because the Ariane 5 put us in such a perfect trajectory, we can use the propellant to go to 200 kilometers. And this means that we will have better resolutions of all the instruments. So that's a big plus. And then the mission nominally will end in March 35, but if we still have enough resources, this might be extended to 37. And to get an idea, all the delta V given by all these gravity assists during the interplanetary tour is about 20 kilometers per second. There's a lot of energy. And we will do many gravity assists also in the Jovian system, which will give us about 35 kilometers per second. And this is the only reason that we actually manage to get to Jupiter with the Ariane 5. So why do we do this, the gravity assist maneuvers? If we had to do it in a direct trajectory, the energy could not be given by the Ariane 5. It's a powerful launcher, but not powerful enough. So instead of needing 3.6 tons of propellant, JUICE would have needed 20 times as much to get to Jupiter, and then almost the same amount to slow down, because you would have a very high escape velocity and you would need to get rid of it. So this is an amount of propellant that you could never fit on a spacecraft. So we went for a different solution, which is the gravity assist. So JUICE will use the planets, Venus and Earth, but even our moon to get to Jupiter, just not only to gain velocity, but also to slow down. Because to go to Venus, which is in the inner solar system, we need to slow down and change the direction. And that's what we did in August. And we needed the Lunar Gravity Assist, even though it's a small body, because that little tweak of the moon put us in the perfect approach to Earth in order to get on our way to Venus. And this is what it looked like. 24th of June, we had to do a correction maneuver, which was only 3 centimeters per second, which is almost nothing. So it shows really the extremely accurate and well done work from our mission analysis and flight dynamics teams. Then we checked out all the instruments, tested the sequences that you want to do at the flybys, did some simulations, and then we started following with the ground stations the spacecraft in real time. And on the 19th of August, we had the flyby of the moon, followed a day later with the flyby of Earth, where we had a 100-degree deflection of the orbit and a reduction in speed. And now we are on our way to Venus. This generated some beautiful images. You might have seen them already online. You can see the monitoring cameras that are actually built to monitoring the deployment of the antennas and the radar. But it's also good to show you the moon. We went at 700 kilometers distance, so that's very close. And you see that luckily still deployed RIME antenna. And this blue blob that you might see here is Earth. And you also have another monitoring camera image here with the Langmuir probes. You can here see the other cameras that we have on board for the navigation, so the navigation camera. And this is our high resolution camera on board of the spacecraft that will take also the high resolution imagery of the moons when we get there. So then after moon, we passed by Earth, where we got the majority of the delta V of the gravity assist. There's a beautiful image there of JUICE passing by. And then we also operated all the instruments, and we can say that all the instruments work well. And we confirm that Earth is an habitable planet. Now, this sounds like a bit of a joke, of course, but it's important because we know Earth is habitable, obviously. But we also saw that all the instruments like MAGIS and SWI detected the building blocks of life as we know it. So water, carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur, as well as ozone and carbon dioxide. So these are all the telltales of life as we know it. And the instruments are working the way they should and detected all this while passing the Earth atmosphere. And also RIME has successfully received reflections from the moon's surface. It was the first ever representative test, because on Earth, you cannot test a 9 megahertz signal because you cannot really find an environment where you can do this without having a lot of reflections from the walls. So it's always a bit of a gamble if everything will work. And we are now getting the first results, and it looks like the instrument is working properly, but it still will take some time to really sift through all the data. So, and now after all this was done successfully, now JUICE is moving away quickly from the Earth and the Moon, which you see here, and the next destination will be Venus in 1 year. And just to give you an idea, all this work doesn't come by itself. It's done by an amazing team of many, many people. So here you see the numbers, but it's more than 2,000 people working since 2014 to build, develop both spacecraft and instruments, launch it and operate it. And we're now well on our way for getting to Jupiter in 2031. So if you are interested in knowing a bit more about the people behind JUICE, but also JUICE itself, on YouTube, you can search for The Making of JUICE, where you have an extensive documentary showing the people working, what their challenges were, also focusing a bit on the difficult times of COVID. So if you're interested, you can have a look and you'll know a bit more. And after all this, I leave the floor to you. If you have any questions, please let me know.
Thank you, sir. It was an amazing presentation. It showed us how knowledgeable and how much of an effort and collaboration various countries across the globe and Europe have committed to the effort of the JUICE mission. So can we proceed with questions from our audiences right now?
Absolutely.
Sure. Dear audience, you can either share your questions in the chat box or you can raise hands and you can go ahead and ask. Thank you.
No questions?
Currently, we're waiting. Sir, we have also shared some questions with you prior to the to this meeting. So, if you'd like to take up on those questions first, that would be nice.
Yeah, I don't have them with me, but if you read them out, then I'll try to reply to them.
Okay, sir. Um,
In the meantime, I can try to answer a few of the questions coming in while you look them up. So there's a question on the sequence that JUICE is going to visit the moons. So when we arrive at Jupiter, we will first dedicate a phase to Europa. We do 2 flybys of Europa. Then we do a high inclination orbit that will focus really on the polar regions of Jupiter. And then there will be flybys also of Ganymede, but also of Callisto. In Callisto, there will be quite a few flybys, mainly as gravity assists opportunities in order to, in the end, get also to the final orbit around Ganymede. And in Ganymede, we will spend about 2 years of our mission really mapping it in detail in a polar orbit. So then there was another question while you're looking up the other ones. Insight on plume activity of Europa and Enceladus and how it would be helpful for astrobiological studies. Now, I immediately give a disclaimer. I'm an engineer, not a scientist, so I can only give a limited answer to this. But the plume activity of Europa, so basically what it is that in the subsurface, we know there is liquid waters and it can be a kind of geysers. Instead of letting out hot steam, it would be kind of fountains of ice coming out, a kind of cryo volcanoes, if you want. And if you were lucky enough to fly through it, you could actually, with the instruments on JUICE, you could measure the composition, so it would give you indications of what's happening inside Europa. For Ganymede and Callisto, this is unlikely because the crust is much thicker. So there's, we don't think there will be this cryovolcanism. But Europa might have it. We know Enceladus, it has been seen. It's at Saturn. But there would be, if you're lucky enough to go through one, you could do measurements and you might know more about the what's happening inside the core, the ice core. JUICE is the mission name, yes. It stands for JUpiter ICy Moon Explorer. It's a bit creative. And the planet is, of course, Jupiter. So why isn't Mars a popular choice for gravity assist? Well, it depends very much when you launch. If we would have launched in 22, which was our original launch date, we actually would have flown by Mars. But it all depends on the moment you launch, the alignment of the planets, where they are, and whether you can use them for flyby. But Mars can be a good candidate. What would have happened if the last recovery attempt failed? I guess is for RIME. Yeah, so this was really the problem, because once you have released all the switches, you have a system that has not deployed but could deploy. So you don't know why it's not deploying exactly. So if it really stuck and it doesn't go anywhere, I think we would have had only a very limited amount of science from the ground penetrating radar, from RIME, because you don't have a dipole anymore. You would have some kind of hybrid between a monopole, dipole. The frequency would be off. The radiation pattern would be very strange. So, of course, we would have tried, and something I'm sure would have been gained by it, but it would be only a fraction of what can be achieved now. I think that we pretty much exhausted all our options. And the problem is, the longer you wait, the higher the risk is that it just gets more stuck. And in time, cold welding, these kind of phenomena. So for us, this was really the last attempt, other than hoping that maybe at some point, maybe at the flyby of Venus, it will get hot enough to just release. But that's a risk by itself as well, because if you suddenly have an uncontrolled release while you're doing other things, you don't know what happens. So this was really important to achieve this, and we were really happy that even though we predicted it, is one thing to predict it, it's something else to actually achieve it. Next question. Can a lander land on Europa? Yes, but it takes a very complex mission, because a lander cannot be something very small. It needs to have a power source, so probably a nuclear power source, and it needs to be able to communicate also with a spacecraft, or directly to Earth would be difficult. So you would need a spacecraft to relay the communication, and then if you want the lander to go through the ice, you need a way to communicate through the ice. So maybe you need a cable and antenna that deploys all the way down. It needs to, until it's under the ice, it needs to withstand all the radiation. If you can design a relay spacecraft, that spacecraft needs to be quite close to Europa and therefore gets a lot of radiation. But the biggest thing is the lander would be big. And in order to get a big lander there, you need a huge spacecraft, a huge launcher. So it would be a very expensive mission, but it is possible. And if you have the means and the money, you can do it. And this is one of the things also that could be a next step. After JUICE and Europa Clipper determine what the chances are of life and maybe good landing places, a next step could be a Europa lander, but it would not be an easy mission. Another question: for a planet like Mars to plan a sample return mission, what would be the best instruments? Well, there you have to look at the Mars sample return mission, that is a cooperation of many countries, under which NASA, but also the ESA. And basically, you have a mission collecting cores like they're doing now. And with the rovers, the NASA rovers, they're leaving them behind. Then you need something to collect them, put them into an ascent vehicle, and then send them back to Earth. So that's quite a difficult undertaking, and that's being studied right now. So the best instruments of a sample return is more, the most important part is what you do is not so much what you measure there on the spot, but is getting the sample to Earth, and then you can use all the instruments on Earth to study it. I see that I missed one question. What is nadir in the module of spacecraft you showed us? So the nadir side depends a bit how you see it, but it's basically when you look down towards the surface of the body you're watching. So nadir is the down-looking side, looking towards the surface. So, yeah, will JUICE spacecraft and Europa Clipper spacecraft work hand in hand? Yes, this is one of the exciting things. So, both will be there around 31. Europa Clipper will even arrive a bit earlier because they will use a more powerful launcher. So they launch next week and will arrive end of 2030, and we will arrive mid 31. And we will definitely coordinate measurements. There's working groups working together between scientists of the two missions, also strategizing what kind of measurements to do together in order to learn more. Okay. Apart from mass constraints, was there any other reason why JUICE uses solar panel? Well, so why did JUICE use solar panels instead of nuclear power system? It's a very simple answer, is that in Europe we don't have the nuclear thermoisotope technology developed for several reasons, but we don't have it. The other reason, because for instance, the US has it, but Europa Clipper still uses solar rays. And the reason for doing this is that there is quite a downside on using nuclear technology, because there is the perception of safety. There is quite a lot of resistance from the public against it, which is important. It is safe to do, but people feel uncomfortable with it. But also it's very limited. The plutonium that you use for it is, for obvious reasons, difficult to obtain. There's a lot of limitations. And even if all that works, it is also still providing you a limited amount of power. And the solar rays that we developed specifically for this, which Europa Clipper is also using, are really optimized for this. But it needs to be said that JUPITER is about the limit. If you go beyond JUPITER, it's highly unlikely that you can get far enough with solar rays. Is there any robot that can help in making spacecraft? That's a good question. Maybe in the future it's something that can be thought of, but of course, what we're talking about, missions like JUICE are extremely complex. There's a lot of happening inside. There is a lot of cabling. There needs to be testing. The testing you need to do properly in a very complex setup that is difficult to do. I take it the question is if you could build the spacecraft in space, like robot as in help make the spacecraft. If the question is, can a robot help building it on Earth? There are certain things that you can do, certain robots that can help, but robots are especially good in doing repetitive work. And missions like the science missions, usually everyone is different. And if you take JUICE, everything is squeezed into very small spaces. It's very difficult to have access. So it's in the end easier to have a person do it than to program a robot, a very complex robot, to do exactly this specific task. Okay, maybe the questions that were asked before, if they are found in the meantime.
Yeah, so regarding the questions, I think everyone has asked all their questions. So the ones which we had sent, should I go for it?
Yeah.
Okay. One of the questions is that Jupiter has the strongest magnetic field of any other planet. What challenges does this pose for the construction of the spacecraft?
Yeah, that's a very good question. Indeed, it's a big challenge because the magnetic field, what it does is it traps particles. And especially there's the moon Io, which is a volcanic, so close to Jupiter, has a lot of thermal activity. So it emits a lot of particles, like volcanism. And these particles get caught into the magnetic field and are charged. And these form extremely strong radiation belts. And the radiation belt is one of the main challenges for missions such as JUICE, is that you need to design your electronics to survive this kind of environment. So basically, you need to shield the components that are not able to survive this kind of environment. We're talking about, without any protection, something that would be exposed is in the gigarad range. So hardly anything is able to survive this. So you basically, the only thing you can do is put material in between. So you have the natural protection of the spacecraft, the tanks, the batteries, etc. They absorb quite a bit, but all the rest you have to do with material, with heavy materials such as lead or metals, in order to be able to absorb all this radiation, so that the components themselves that maybe can only survive 20, 30 kiloreds will be able to survive the whole mission.
All right. I'll go for the second question. Juno protects its electronics in a vault. Europa, Clipper, and JUICE do not. So Clipper had a scare. So what do you think about the same happening to JUICE as well?
Yeah. Maybe a small correction. JUICE does have the vaults, as I explained before. So we need it. Without the vaults, we would really be in trouble. But even despite this, there is still a significant amount of radiation that the components are going through. Now, without going into too much detail for Europa Clipper, basically the scare that they had was that certain components were flagged as maybe not being able to withstand the environment. And this was studied in more detail, and it was more the way that the tests were done. They had to be accelerated to limited time, but this acceleration created a bit of a unrealistic environment. So the tests were showing failures that would not happen in the real mission. So it's always a concern when a warning is issued, and we also followed it up closely, because there are certain components that we also have that could have been affected, but in the end it was of limited effect. And indeed, you can see that Europa Clipper will launch next week. So they also concluded it was okay. But it's always uncomfortable when you hear these kind of warnings, especially when you have already launched, because the only thing that you can do is change your trajectory to stay further away from Jupiter, and therefore reducing the radiation. But it looks like this will not be the case.
All right, thank you for that. My next question is, how can young students, particularly bachelors in the aerospace field, upskill themselves for the contributions in the aerospace field? And how can a student keep going?
Okay, so two questions. How can you keep going? I think is motivation. If you know what you want to do, if you have a goal that you want to achieve, even if things are difficult, you can move beyond it. So I think it's important to choose a direction, a discipline that motivates you. If that's the case, it's easier to keep on going, even if it's difficult. Right. In order to prepare yourself properly for missions like these, but this is valid for many other disciplines, I think it's important to go to industry for some time, and to really get familiar with a subsystem in detail. Especially if you look at system engineering, you cannot be an expert on every subsystem, but it's good if you choose at least one subsystem and study it in detail, so that you know that behind every subsystem there's a whole world of challenges, of complexities. And once you are aware of this and you know how to solve these problems, you are more equipped in order to also approach other subsystem issues. And of course, you need to be surrounded by very competent people who are experts on the field. But I think that in order to be prepared for a job in the space industry, it's good to first look at something in high detail. And with that knowledge, you can move further.
All right. Thank you. That was a very nice answer. Moving on. from someone who doesn't belong to one of the ESA member countries, how can they join ESA?
Well, there is always the option of working for contractor companies. So you can do work, but so if you want to become staff, you have to be part of the member states. But as a contractor, and there are opportunities for contractor positions, then you can work for ESA. So you have to keep an eye out for vacancies issued by contracting companies.
All right. Next question is, what techniques can be used to analyze the thin atmospheres of moons like Europa and Callisto, and what can they tell us about surface and subsurface processes?
I think this goes a bit in the direction of what I answered before. Again, I'm not a scientist, so the real detailed answers lies with the experts that really know how to interpret the data. But basically, you have different kinds of instruments. You have the in situ instruments that measure the particles and the energy fields around the spacecraft close by, and you have the remote sensing instrumentation. Remote sensing like radars, laser altimeters, etc. So in order to study the thin atmospheres, what you would like to do is with the in situ, the particle physics experiments, really measure the components, measure the energy levels, measure the composition, and by getting these data, so from these measurements, then on ground you can analyze it and you understand better what's happening, both on the surface but potentially also under the surface, depending on how much interaction there is between the surface and the subsurface.
Thank you so much, sir. These answer my questions. I think the number of questions have ended, so I'll be handing it over to Prathamesh right now. Thank you.
Okay.
As we conclude today's webinar, I would like to thank Mr. Alessandro for sharing such a valuable insights and expertise. Your presentation has been truly inspiring and informative, contributing to our celebration of World Space Week. We deeply appreciate your time and efforts, and we look forward to collaborate with you in future again for Venus, definitely for the Venus mission, and many more to come. Thank you so
Absolutely.
much. I would like
Thank
to
you for
take
your
this.
attention.
Yeah, I would like to take this moment to thank my colleague Mihala because of this webinar was possible, and thank you so much.
You're most welcome. Thank you. Thank you for your attention.
I have a question.